But actually, we talked about the Milky Way galaxy was the first chapter in this unit. So generally know the anatomy of the Milky Way galaxy. I kind of circled a couple, like know it's 100,000 light years, and know that we're actually 27,000 light years from the center. And these actually are posted under doc sharing, this document that I'm going to kind of be walking through. Let's see, what else do we have? Let's see. Oh, I guess the other thing, still back to the anatomy of our galaxy, the slide next to kind of the disk, the edge-on look, looking at it face-on, know that there's types of stars. There are the halo stars, and they're the disk stars. Okay, know that there's a nuclear bulge in the center of our galaxy. The next ones, what are the large and small Magellanic Clouds and the Sagittarius and Canis Major Dwarfs? Those are actually cute little galaxies that are associated with our galaxy. In the case of the first two, they are orbiting us. In the case of the last two, they're merging with us. The next one, how do we see through all the dust and gas in our galaxy? And so I brought in up there at the top there kind of the strips. I don't know if you remember. Each strip actually is a different wavelength. So we look at different wavelengths is how we see into our galaxy. The next one is how do disk stars and halo stars orbit the galactic nucleus. That's this one over here. Basically, the yellow are the disk stars, and they're nice and orderly, and the green are kind of the random halo stars, the wild children. I think we talked about that clear back in Unit 1. Location of dark matter in our galaxy, that's actually a figure that we looked at just a little bit ago. That little orange thing actually is our galaxy, and kind of around our galaxy, of course, the disk of our galaxy, we have some halo stuff. That's fine. But kind of that sort of spherical looking gray stuff, that's actually dark matter. And then how did we determine the dark matter? And actually this goes, I know this is chapter 15, but actually we revisited it in chapter 18. It's by how fast the stars and dust were orbiting our galactic nucleus. It didn't slow down like our solar system. The next one, interstellar bubbles. And the way you look at this little image right here, it looks like a pimple. But this kind of white-looking thing, actually, that's the disk of our galaxy. This is the disk of our galaxy. And this interstellar bubbles, basically, is one of the things we said that stars blow up, whether, massive stars go supernova, okay? And the material kind of blows outside the disk, and then it falls back in. That's it. Okay. Galactic recycling, seems like we've kind of, that's we're all made of stardust sort of thing. But here's a figure from that chapter on galactic recycling. Remember, galactic recycling and star cycle is the same thing. The ultimate result, I wrote in blue under there, that basically we end up with less gas and more heavy elements. Ionization nebula, remember what a nebula is? There's a region of gas and dust, but an ionization nebula is basically glowing because it's got those hot stars there. And remember we talked about 7 types of stars, and the hottest are the O and the B type stars. Sagittarius A star, of course, is that supermassive black hole in the center of our galaxy. That's where it is, and that's what it is. And how do we know it's there? Actually, this one right here, these actually little dots are all like looking at the movement of stars around. That hash mark is the center of our galaxy. So based upon how fast they were moving, we could get a fix on the mass there. And we knew it was confined to a small enough area. It must be a black hole. All right. The next chapter on galaxies in general. How many galaxies are in an observable universe? About 100 billion. Smiley face. Different types of galaxies. Okay, there's the Hubble tuning fork diagram. But remember, we have spiral galaxies, elliptical galaxies, lenticular galaxies, and irregular galaxies. So I kind of have a little note about each. In purple, I say the spiral galaxies, there's a disk with spiral arms. Elliptical galaxies, I said in purple actually on the other side, there's no disk. They're all halo. That's what ellipticals are. In red, the lenticular galaxies are disk but no spiral arms. And irregular galaxies are neither disk nor rounded. Standard candles, they're objects that have a well-known luminosity, or how much energy they're putting out. And we use them in astronomy to basically understand how far away that standard candle is. So we know that we can say distance is equal to the square root of luminosity divided by 4 pi times the apparent brightness. So basically, the dimmer it is, the farther away it is, okay, as compared to its luminosity. Examples of standard candles would be that main sequence fitting, Cepheid variables, white dwarf supernova. Measuring the distance to Andromeda, of course, he used a Cepheid variable, and he used the technique of Cepheid variable as a standard candle. Expanding universe, Hubble's plot, Hubble's law. Expanding universe we can get from the motion of galaxies. Hubble's plot was this. What did he do? Well, along the x-axis, that's actually distance of the galaxy from us, and along the y-axis is how fast it's moving from us. So Hubble's law says the farther it is from us, the faster it's moving from us. So determining distances using various techniques looks like this. There's radar, then there's stellar parallax, and then there's main sequence fitting for stars in our galaxy. But 4, 5, and 6 are the ways that we get to distances for galaxies. Cepheid variable in a galaxy, white dwarf supernova in a galaxy, and Hubble's law in a galaxy. Cosmological horizon, looking back toward before the universe existed. Cosmological redshift, that was with the balloons. Basically, as the universe expanded, the fabric of space and time expanded, so wavelengths in that fabric actually were lengthened. Observing evolution of galaxies. Remember, the way this figure worked is over on the left, those were our galaxies shortly after the Big Bang. They're the farthest from us. And then over here on the right are the galaxies that are closest to us, and they are the oldest ones. Cosmological collisions, or galactic collisions. We have a couple of different options with galaxies kind of interacting with each other. They can merge if they're similar sizes. We call it cannibalism. If one's big and the other ones are small, they're kind of they're coming together, okay? But one's big. And then the starburst actually is where you have a pair of galaxies that just kind of the way they interact, they cause a bunch of stars to be born all at one time. That next one, the formation of spiral versus elliptical galaxies. Actually, I have two little figures up there. Remember that we said there's a deal with rotation. Okay, the top one is rotation. If it's rotating, you get a spiral galaxy. If it's not rotating, you get an elliptical galaxy. Then there's also a thing with density. If it's very dense, you get an elliptical. If it's not very dense or sparse, you get a spiral. And then quasars. Whoops. What did I say about quasars? Quasars are a feeding black hole. Quasars. I guess I didn't say anything about it. The quasars are a feeding black hole. All right, next chapter. So now this is on the Big Bang. So generally know what a Big Bang, the Big Bang theory says that basically the universe started out as a dense, hot object we call singularity and has been cooling down ever since. The four physical forces that we have today that had to have been at least kind of separated at the time during the early on in our universe: gravity, electromagnetism, strong force, and weak force. The gut force in the gut era, okay, the gut force is everything but gravity. Okay, that's how I remember it. Quarks, actually draw a line through that one. I'm not going to have anything about quarks. Era of nucleosynthesis, how long did it last? 5 minutes. The next one, actually, in the video and in my notes, but the video talked a lot about this time when the universe became transparent. And after the Big Bang, that's about 380,000 years. And the reason it became transparent was because basically the electrons settle down and associated with nuclei. Okay, so kind of from left to right, the orange is where you have a bunch of electrons not having homes. It cooled down so the electrons could form atoms. That's why we call it the age of atoms. It began with about that time. Basically, they found homes around the nuclei. The next one, the cosmic microwave background, is the signature. Energy is the E, energy signature of the Big Bang, CMB. And actually the next one's the same thing. Cosmic microwave background and cosmic background radiation, it's the same thing. Who discovered it? Penzias and Wilson. Remember the pigeons, okay? Pigeon droppings. What temperature and actually is that radiation now? It's about 3 Kelvin, which is very cold. How is the radiation distributed? Pretty much uniformly. And what they call uniformly means as a word for uniform means is isotropically. Inflation is actually you had a homework question for this chapter. What is inflation? It's that sudden expansion of the universe early on. Evidence of the Big Bang, there are 2 things. There's the cosmic microwave background, and the other evidence for the Big Bang is the amount of hydrogen and helium, about kind of a 3-to-1 relationship in the abundance in the universe. And the last one, Olber's paradox, basically asks the questions why at nighttime are our skies black instead of basically lit up with stars. And so that's the question. And the answer is because our universe had a discrete beginning and it is changing over time. Then the last one we just did, dark matter, dark energy, what do they have in common? Well, they're dark. You just really can't specifically see them, but you see their influence or their effect. How do we detect dark matter in our galaxy? Remember, we look at basically the gravitational influence of dark matter on things as they orbit our galactic center. How is dark matter distributed in a spiral galaxy? Similar figure to before. Around a galaxy, it's kind of like an amniotic fluid. It's like the one video we saw said, basically it's kind of a scaffolding that the galaxy formed in. Gravitational lensing is where you have a cluster of galaxies, basically, and their dark matter forming kind of a dent in the fabric of space and time, such that light will be bent by it, and we can actually see objects behind the cluster. Options for dark matter, that would be the machos and the WIMPs. Machos are the normal baryonic material. What sort of could create the normal stuff? Well, we could have brown dwarfs, other massive stuff in the halo region. WIMPs are weakly interactive massive particles. How are galaxies organized? They're organized in clusters, and actually clusters are organized in superclusters, but they are formed on galaxies are formed on filaments around void areas. The 4 models of the universe look like this. The youngest model would be the recollapsing one. The oldest model would be the one we believe is currently to be the case, the accelerating universe. Cause of acceleration is dark energy. And that is that. So I guess we'll meet you here on Wednesday.